is the angle the field makes with the plane of the coil. Now, we also talked about induced EMF in a rotating disk. And we came up with an expression E equal to induced EMF E is equal to pi B pi R squared F, where B is the flux density normal to the coil, and then R squared is the length from the center of the disk up to the rim, or you can call it the radius of the ring. Then F is the frequency. And we derived that expression, and it is upon that expression that the following activities were given. But we also talked about Lorenz's disk method of determining resistance absolutely. So we concluded with 2 activities. Now let's briefly talk about activity 1. Question 1A was saying a metal disk of radius A or alpha is placed in a magnetic field of flux density B with its plane perpendicular to the magnetic field. The disk is rotated with uniform angular frequency F. We had to derive the expression for the induced EMF between the rim and the axis of the disk. That one we are not going to repeat because it is exactly within the notes that we had handled. Now part B, there was a circular disk, aluminum disk of radius 30 centimeters, is mounted inside a long solenoid of 2000 turns per meter, carrying a current of 5 amperes, such that the axis is along the axis of the solenoid. If the disk is rotated about the axis of 40 revolutions per minute, find the induced EMF. So the fact that we are talking about a rotating disk, the expression is going to be E equal to B pi R squared F. You will note that everything was given. The magnetic flux density was given to be, we have if it is for a solenoid, that means the magnetic flux density is for the solenoid. So that means we are now going to have B is that where B is equal to mu naught Ni for the solenoid. And therefore, if we substitute in here, so it is going to be equal to mu Ni, then pi R squared F. So we substitute, that is 4 pi times 10 power minus 7. The number of turns per meter in this question was given to be 2000 times the current flowing in the solenoid is 5 amperes. Then pi times pi, the radius was given, the radius of the solenoid of the coil or the disk is 30 centimeters, 0.3 square, times the frequency, and the frequency was given to be 40 revolutions per minute. 40 revolutions per minute, so we divide by 60. And I think in the end, we are most likely to get the required answer in volts. Now members, these exercise activities that we give you, want you to practice them. When you don't practice them, then the essence of the exercise will be rendered useless. Now you also need to note that the only way I'll know that you are doing some work is for you to submit the work. I gave you the WhatsApp number. so that I can see some of your submissions and see that you are following. It is only, I got only one response from the previous work. It is only Omegon who tried to present something, but others are extremely very silent, so I'm not aware whether we are following or not. So send in your submissions, appreciations, comments. If you want clarifications, you can present them so that we learn in a group. So question 2 was saying, that is in activity 1, uniform copper. There was a uniform copper I'm sorry, I'm making some small adjustment here. The question was saying, a uniform copper disc of plane area A placed between poles of a U-shaped magnet with its plane normal to the field of flux density B. The disc is then spun about the axle at a frequency f. Derive an expression for the EMF induced between the axle and the rim of the disc. That one, we are still going to take you to the previous derivation. If the radius of the disc is 2.5 centimeters, a magnetic flux density in the region of the disc is 0.84 Tesla, and the disc is rotated at 300 revolutions per minute, what is the magnitude of the induced EMF across the disc? You're going to realize that the working is going to be the same. So you're still going to say induced EMF in a disc is equal to B pi R F, B pi R squared F. According to what we have in the question, the magnetic flux density was given as 0.84 pi. The radius of the disc is given as 2.5 centimeters. We can convert to meters and then square times the frequency 300 revolutions per minute. It is 3,000 actually revolutions per minute, so we divide by 6 to convert to revolutions per second. And then finally, the answer is going to be in volts. I did not evaluate, but you can press your calculator and then get the exact answer. So that was 2A. Then 2B, a circular metal disc of radius 10 cm is mounted at the center of a long solenoid, 500 turns per meter. The solenoid is connected in series with a resistor R, which carries a current of 0.2 amperes. The disc is rotated about the axis of the solenoid at 100 pi rads per second. The induced EMF between the center and the rim of the disc balances the PD across the resistor. Then calculate the value of R. Now you realize that such a question is actually talking about the Lorentz disk method of determination of resistance. We can use first principles, or we can simply substitute in the expression directly. We say at equilibrium, PD across the resistor is equal to induced EMF in the disk. Induced EMF in the disk. So that means here IR is equal to the induced EMF in the disk, which is B pi R squared F, where the fact that we are using a solenoid, B is equal to mu naught Ni. So that means this expression turns out to be equal to mu naught Ni B pi R squared F. So the current can go, so we end up obtaining R to be equal to mu naught Ni N B pi r squared F. And that is the expression which we got previously. So you can now substitute in our expression. This one turns out to be 4 pi times 10 power minus 7. The number of times per meter according to this question was given to be 500, 5,000. Then magnetic flux density, the B was substituted. So here the B does not exist because it was substituted here. So we only have pi, the radius of the disk. According to this question, the radius of the disk was 10 centimeters. So we convert to meters and square. Then the frequency was given to be given in terms of rads. You know, W is given as 100 pi rad per second, but you know that this is going to be equal to 2 pi F. So that means F is going to be equal to, because these rads will go, so remain with F is equal to 50 hertz, or revolutions per second. So this is going to be 50. So we can now substitute it and then get the value of our resistance. So question 3, figure below showed a bicycle wheel with several spokes, each of length 30 centimeters, span about the axle normal to the horizontal of 420 revolutions per minute in the Earth's magnetic field of flux density 3.0 times 10 power minus 3 at a location where the angle of dip is 30. Now here on number 3, this is number 2. Number 3, what we mean by angle of dip? Angle of dip is the angle between the resultant Earth's magnetic flux density, magnetic flux resultant Earth's field and the horizontal. Now you will do well to note that the Earth is a sphere. It has a magnetic meridian, a geographic meridian, and what we call a magnetic meridian. The magnetic meridian does not lie exactly along the Earth's field. Earth is geographic pole. So the horizontal or the equator is this way. So the angle the resultant Earth's field, or what we call the magnetic axis, mixed with the horizontal, is what we call the angle of dip, the Earth's field. So the field will be moving from north to south, or from south to north, no matter. So that is the angle we are talking about. So that means in the Earth's field, we have the resultant Earth's flux density is a hypotenuse that has two components. It has the horizontal component and the vertical component. So that means if this is the Earth's field, the resultant Earth's field, it has two components, the horizontal component of the resultant Earth's magnetic field and the vertical component of the Earth's magnetic field. So the angle it makes with the horizontal is what we call the angle of dip. The angle of dip. Now you do well to note, according to that, to our question here, that the Earth's field is making an angle the disk is being threaded by the vertical component of the Earth's field. So that one implies that it is the B vertical that is threading. So we want to get the component of the vertical component that is threading the coil. This is bicycle disc or bicycle wheel. So therefore, induced EMF is equal to B vertical pi r squared F. Now the vertical component is opposite to the angle. Therefore, B vertical is equal to B sine alpha. So we substitute in this expression here for B. It's going to be B pi r squared F sine alpha. And then we can substitute in the values that was given by the question. I'm sorry, there is some little technical thing here. You wait for around 3 minutes. Okay, we are back. We are sorry for that technical interruption. We are saying that the induced EMF in the bicycle wheel is given by B pi r squared F, but it's the vertical component that we're threading. We're threading the wheel, so you can now substitute in the expression. The B, according to the question, it was given at 3.03 times 10 power minus 3. Then times pi. The radius was given to be 30 centimeters, which is the same as 0.3 squared, times the frequency was given to be 400 revolutions per minute, so 420 divided by 60. Then times sine, the angle was given to be 30, sine 30, that's the angle of dip. And then you can evaluate. I think we are most likely to get an answer of 3.0 times 10 power minus 3 volts. Or we can simply say that this is 3 millivolts. So that is how we had to work that one out. Now we go to the second activity. Activity 2. We did activity 2 after handling induced EMF in a rotating coil. And we said when we are handling induced EMF in a rotating coil, we said that if this is our coil, and this is the magnetic field, the angle of our constant, this is the normal to the conductor. This is the plane and this is the normal. And the angle of our constant is the angle the normal makes with the field. So therefore, component of the magnetic flux density normal to that one is going to be equal to B cos component of B normal to the coil is B cos theta. So from Faraday's law, induced EMF, we said is equal to minus d phi, I'm using capital, by dt, where capital phi, which is the flux linkage, is equal to NAB. So we said when we substitute in the expression, we said that it is the field that is changing. So that means the N is constant, the area is constant, it is only the B. So you can simply say, it's only the angle that is changing, so that's going to be NB d by dt. Cos, we substitute that cos by Wt, so it becomes cos Wt. So the negative is still existing for that one. So therefore, that one, we first differentiate the angle, so it become WNAB. Then we differentiate the cos, we get negative sign, Wt. The negatives cross, we end up having W now, sine Wt. Turns out to be the expression for the induced EMF, which is the same as E naught sine Wt, whereby the peak value, E naught turns out to be W naught. So my major concern is to know at all times the angle that we are talking about. So if you are given, for example, that angle, then the other angle will subtract 90 from it. Now, let's go to the first activity and see exactly what our interest was. So question 1 of the second activity was saying that a coil of 100 tons, area 2 centimeters, 2 times 10 power minus 2 meters squared, lies in a magnetic field of flux density 3 times 10 power minus 3 Tesla, and rotates uniformly at 100 revolutions per second about an axis perpendicular to the magnetic field as shown in the diagram. So calculate the induced EMF when the plane of the coil makes an angle of 60 degrees with B. Now we are told that the plane of the coil is making an angle of 60 degrees with B. If that is the coil and that is the magnetic field, the plane is making an angle of 60 degrees. But usually our interest is the angle the field makes with the normal. So we can now trace our normal N, and therefore the angle the field that makes with the normal is going to be equal to 90 minus 60. That is our angle of interest. And therefore, when we are using the expression E, the first part of the question is requiring us to use E is equal to the expression that is going to be E naught sine Wt. The E naught is W now, so that's going to be equal to according to the question, we're given that the angular velocity was given to be 100 revolutions per second. This is going to be 2 pi f now, sine Wt. That's going to be 2. This is 100. The number of turns are 100. And then the area of the coil was 2 times 10 power minus 2. The frequency was 100 revolutions. Now then the area is that magnetic flux density B was given to be 3 times 10 power minus 3 Tesla. Then sine 30. It's going to be sine 30. That is 90 minus 60. So we end up getting the answer that was given as 1.885 volts. That is number 1, Roman 1. Then Roman 2, we are given, we want to get the amplitude of the induced EMF. That one is going to be straightforward. E is equal to W naught, and that is going to be equal to 2 pi F now. That is 2 pi. The frequency was given 100. The number of times are 100. The area is 2 times 10 power minus 3, 2. And then the flux density 3 times 10 power minus 3. And the answer, we end up getting 3.77 volts. So that is in as far as question 1 of the exercise was concerned. Then we go to number 2. A flat circular coil circular coil each of radius 10 rotated at a frequency of 200 revolutions per minute about its diameter at right angles to a uniform magnetic field of flux density of 0.18 Tesla. We are to get the maximum flux linking the coil. The maximum flux linking the coil. So flux is just going to be equal to now. Maximum when it is sine 90. So we just substitute in the expression. So that is the number of turns were given to be 500. Then the area of the coil was given to be given the radius, which is pi. Our radius is 10 centimeters converted to meters and square. And then the magnetic flux density was given to be 0.18 Tesla. So we end up getting the maximum flux to be 2.83, you can confirm, Weber. Then induced EMF in a coil when the plane of the coil makes an angle of 30 with the field. The plane makes an angle of 30 with the field. So if this is the plane of the coil, and this is the magnetic flux density, it makes an angle of 30 degrees with the field. So meaning that the normal makes an angle of 90 minus 30, giving 60 degrees. So therefore, our interest therefore turns out to be that induced EMF is equal to W naught sine WT or sine theta for that matter. So that's going to be, according to what we have, the angular velocity was given to be 200 revolutions. So we convert this one to 2 pi f now sine theta for that matter. So 2 pi, the frequency was given to be 200 revolutions per minute, divided by 60. Then the number of turns in the coil is 500. Then the area, of course you had noted it to be times 10 power minus 2. Then the magnetic flux density is 0.18 sine 60. So we substitute and then get the final expression. I predict the answer will be 551.3 volts. You can verify the answer. Our interest is not much about the answer but the working. If we are convinced with the working, then we can now proceed. So this is number 2, Roman 1, Roman 2. Then we got Roman 3, the root mean square value of the induced EMF. From your AC circuit, we had said that VRMS is equal to V naught over root 2. Similarly, ERMS is equal to E naught over root 2. So we can now come and substitute in the expression. So we end up having ERMS is equal to E naught over root 2. But originally, this is the same as W naught over root 2. So the expression is only substituting it there. That is going to be 2 pi f V is 200 over 60 times 500 times the area times 10 power minus 2. The flux density is 0.18 Tesla. So we can now divide by root 2. And I suspect that you may get an answer of 41.9 volts. We got the last part of the assignment. You can mark yourself and see whether you are on the right track or not. And then, if anything, you can now submit your request for clarification, comments, or if the explanations are not convincing, we can find a way of fixing it slowly by slowly. Then, the last question. A rectangular coil of 50 tons is 5 centimeter wide and 30 centimeter long. If it rotates at a uniform rate of 300 revolutions per minute about the axis parallel to its long side, and it's at right angles to uniform magnetic flux density of 0.4 Tesla. Find the peak value of the induced EMF. Peak value of the induced EMF, E naught is equal to W now. Now, according to what we have, W is given in terms of frequency, so it's going to be 2 pi F nav. Then 2 pi frequency, according to what we have, 3,000 revolutions per minute. We divide by 60. The number of turns of the coil we are told so the number of turns were not given, maybe it was skipped. And then the magnetic flux density is 0.04. Then the area, I've forgotten, I skipped the area. The area is 15 centimeters by 30 centimeters. Convert to meter square. Then times the magnetic flux density of 0.04. We can take the number of times to be 1. And then we can find a way of getting the final expression. So now, that is in as far as induced EMF in a rotating coil is concerned. Now, our interest today, we want to talk about application of induced EMF in a rotating coil. And generally, we are going to be talking about only 2 applications. The first one is the AC generator, which you call the alternator. And the second one is a DC generator, or what you call a dynamo. Unfortunately, I was meant to play a small video on see how the AC generator works. So what we are going to do, we will try to attach this video in your notes as you are reading through after the lesson. As you are reading through, you'll be seeing the actual animation of how the coil is rotating in a magnetic field. Why do we say that at maximum, when it is vertical, the induced EMF is 0, and when it is a horizontal one, the induced EMF is what? Is maximum. Now, you were going to note here that the intention of this instrument, AC generator, is to generate EMF.
In this module.
Is to generate what? EMF. Using a rotating disk electromagnetic induction. So the diagram looks this sort. You can have this as North Pole. And then you can have something of this sort. South Pole. Then here we have one long one and then the short one. So this is coil ABCD. CD. So ABCD is a rectangular coil. Then NS, pole pieces of a strong magnet. Then we have B1 and B2. These are carbon brushes. Then we have S1, S2. S1, S2. These are slip rings. So, when you are told with the aid of a diagram, describe how an AC generator works, you can draw a simple diagram like that one. And in the diagram, we are not minding about the beauty of the diagram. Our major interest is the labeled parts. So we will look for at least any 4 labeled parts. You would have described labeling, drawing, and labeling the setup. You would have described the structure of that instrument. Action. How does it work? We normally put something to rotate the coil. And that's why we are indicating here axis of rotation. Of rotation of the coil. So we're now saying when the coil is rotated in a magnetic field, when the coil is rotated in a magnetic field, the flux linking it changes and an EMF is induced. And the induced EMF rotates in the direction A, B, C, D, depending on the direction of rotation of the coil. Now the resulting current is led away through the carbon brushes B1 and B2 to the load. Now we are saying when the coil is in the vertical position, as will be illustrated in the video, EMF is 0. As AB begins to move downwards and CD upwards, EMF reverses in the coil. Now since the rings S1 and S2 maintain contact with the same carbon brushes B1 and B2 respectively, current also reverses in the load R. Hence the current supplied to the rod R is an alternating type of current. And therefore, even the graph that we obtain is going to be alternating, sinusoidal in nature, indicating alternating current. This is induced EMF and that is time. I'm not going to dwell much on that one. The video will give you more clarification beyond what I've just said. And the fact that we are just revising, you just simply look at the video for more clarification. Then, a DC generator. They are only differing in structure. The essence is to produce current. Now we are going to realize that we are going to draw a rectangular coil like this. Sorry, let me make a better diagram. This is like this. So this is now going to be done like this. This is north, south. Then we can use slip rings, split rings, or what we call commutators. So this is A, B, C, D. ABCD is a rectangular coil. These are C1, C2, B1, B2. NS, 4 pieces of the strong magnet. Then B1, B2 carbon brushes. Then C1, C2, these are commutators, or what we call split rings. And then R is the load. The load could be any gadget. It could be a voltmeter, could be an ammeter, could be a galvanometer, could be a bulb, could be a torch, could be a radio, or anything that is going to detect that an EMF has been induced. We'll call it load R. Then ABCD is a rectangular coil. It's a rectangular coil. The principle is the same. We are going to say that we are having magnetic field moving from north to south, and therefore when you make the coil rotate in a direction shown, that is the axis of rotation, the coil cuts the magnetic field. So when the coil is rotated mechanically with a uniform angular velocity to cut a uniform magnetic field, the flux linking the coil changes and an EMF is induced. And the resulting current is led away via carbon brushes B1 and B2 to the load. In the vertical position, when the coil is in the vertical position, as it is going to be illustrated in the video, the induced EMF is 0. The induced EMF is 0. Why are we saying that the induced EMF is 0? It is because the normal is going to be parallel to the field. And remember, our angle of interest is the angle the field makes with the normal. So if it is in the vertical position, if the coil is in the vertical position, it implies that the normal to the coil is this one, and this is the normal. And the magnetic field is also in that direction, meaning that the angle the field makes with the normal is 0. And therefore, there is no induced EMF. Sine of 0 is 0. There is no induced EMF. So in the vertical position, the induced EMF is 0, and maximum when it is horizontal. So you're saying as AB begins to move downwards and CD upwards, EMF in the coil reverses, and at the same time commutators change contact with the brushes. Now since the commutators lose contact with the carbon brushes when the coil is in the vertical position, the output EMF is maintained in the same direction, hence direct current. And therefore, the graph that we deal with in this case is going to be in only one direction, indicating direct current has been induced. Against time, in seconds. So that second graph is not sinusoidal. We are saying AC generator can be converted to DC generator by replacing the slip rings with the split rings. Split rings are the commutators. That is the major difference between AC generator and the DC generator. But we also need to also note that AC generator produces more EMF than the DC generator, as we have noted. Then, I think those are the major applications of induced EMF in a rotating disc. Now I want to end our lesson today by talking about eddy currents. We are meant to have talked about eddy currents and motors, but at the time when we are covering motors, we had not talked about induced EMF. So the details of that induced EMF was still pending. So that's why we delayed to talk about eddy currents. Eddy currents. Now, what are eddy currents? Eddy currents, these are induced currents in a metal. These are currents induced in a metal conductor whenever there is relative change in the magnetic flux linked with the conductor. In other words, whenever there is change in the magnetic flux density linking a given conductor, there is eddy current that circulates within the loops. So therefore, eddy currents flow in a conductor in such a direction to oppose the change that caused them to flow. In other words, they flow in a direction opposite to the applied field. Therefore, how do we produce eddy currents? In a motor or in any given conductor, like in a galvanometer? We are saying when the coil rotates in the magnetic field, the core onto which the coil is wound rotates in a magnetic field. The changing flux linking the core induces an EMF in it. This EMF causes the current loops to circulate in the core in such a direction to oppose the rotation of the core. These current loops are what we call eddy currents. Now we're going to note that eddy currents have two major properties. One, they flow in such a direction to oppose the motion. Two is that they cause a heating effect. And you are going to see most of the users of eddy currents are going to be employing any one of the two properties. Now, something little to note is that eddy currents can be reduced by laminating the core so that the field does not reach the conductor easily. By laminating means we are trying to slot the body of the conductor such that we reduce the number of loops with which the eddy currents have to exploit. And why are we interested in reducing eddy currents? Because of mostly the heating effect. So if this is our given conductor of this kind, so we can decide to slot it like this. And this slotting of this nature, and such that the body is reduced to this extent. Such that the effective body remaining is this. So this is what we call laminating the core. So the shaded area becomes the effective body through which the eddy currents need to circulate, other than using the whole body of the conductor. So that's how we can, that process is what we call laminating the core in order to reduce the eddy currents. Now, application of eddy currents. We have mainly 4 applications. There could be others that could be induced. One, they are used in damping in a moving coil galvanometer. You know what I mean damping? Damping is providing an opposing motion in order to stop the rotation of the pointer. So we are saying the coil of the pointer is wound on a metal frame. When the coil is made to rotate in a radiomagnetic field, of course the flux linking it changes, and EMF is induced and consequently eddy currents flow. So a large eddy current is induced in opposition to the rotation of the pointer. This makes the pointer attain equilibrium position without oscillating many times per second. In other words, the current that is urging the torque within the coil is moving in one direction, and the eddy currents are forcing the pointer to move in the reverse direction. So at equilibrium, the pointer settles in one position without oscillating many times per second. 2 electromagnetic brakes. Mainly this is for the train. So we are saying if the field, the magnetic field is applied suddenly to the wheels of the train, an EMF is induced because the wheels are in motion and they are acting on the magnetic field is acting on the moving wheels. So the flux linking them changes and therefore an EMF is induced. Consequently, eddy currents flow in such a direction to exert an opposing torque to the rotation of the wheel, thereby making them to stop. 3 is the speedometer. Speedometer, or generally speed meter. He said in a speed meter, there is a small magnet inside the speedometer that is producing a changing magnetic field. The eddy currents are set up in the drum onto which the pointer is attached, and the pointer indicates the speed upon attaining equilibrium. So that is the third application. The fourth application, and the last one, is that they are used in induction furnace. I hope that we understand what we mean by furnace. Tannoor, or any structure with extremely high temperatures. So we are saying heating effect of eddy currents is used in induction furnaces for melting metals. We are saying the crucible is a metal container. Containing the metal to be melted is surrounded by copper coils fed with high frequency alternating current. The liquid flowing through the tube constantly keeps pulling it. So the rapidly changing magnetic flux linking the metal parts in the crucible induces eddy currents in the metal, which cause them to heat up and therefore melt. After melting, then we can subsequently get different shapes for the different desired metal. Disadvantages of eddy currents. 1. Eddy current lead to energy losses in the form of heat, that is I squared R, in either transformers, electric motors, galvanometers, etc. We also say eddy currents oppose motion in accordance to Lenz's law, i.e. causes undesirable damping in ballistic galvanometer and other galvanometers that will not be required. So, in brief, eddy currents have 4 major applications. 1, damping in moving coil galvanometer. 2, they are used in speedometers. 3, they are used in electromagnetic brakes. 4, in trains. And 4, they are used in induction furnace. So those are the 4 major applications. The questions normally brought there list any 4 or any 2 applications of eddy currents, or describe any one application of eddy currents, any one application of eddy currents, and then how are eddy currents minimized or how could he minimize eddy currents? Now, experiment to demonstrate damping effect of eddy currents. Experiment to demonstrate damping effect of eddy currents. Don't worry, we are about to conclude. So, if you have a magnet here, another magnet here, so we are saying a metal plate, can have a metal plate. So we are saying a metal plate is suspended in a magnetic field. So remember, this is a magnetic field. It's suspended in a magnetic field, and metal oscillates so that as it does so, it casts across the magnetic field. So the time taken for the oscillation to die out is measured. So you measure the time for the oscillation to stop. You can note that time to be T1. Then you drill holes. You either drill holes in the metal plate or slot it. You can either drill holes or slot it, or make some slots in it. Then, when you drill holes and then you repeat the process again, the oscillation, you also note the time taken for the oscillations to die out. You are going to note that the oscillations are going to be longer. The oscillation after drilling holes in a metal plate are going to take a longer time. If after drilling the time is T2, we are going to realize that T2 is going to take longer. In other words, it is not going to be damped as the other previous one. So, hence, we have demonstrated damping. That we have more damping when the metal plate is not having slots, meaning that there is large eddy current circulating within the body of the metal. And when you put holes, you are reducing the number of loops with which eddy currents has to exploit in order to flow. And it is the eddy current that is responsible for damping the motion or damping the oscillation of the metal plate. So once you reduce the amount of eddy currents, therefore, you are reducing damping, and therefore it's going to oscillate much more than previously. Then, we want to end with some worked examples. So, the first question. Explain why a metal experiences resistance to motion when pulled in a magnetic field. Explain why a metal experiences resistance to motion when pulled in a magnetic field. Part B. A pendulum made from conducting material is made to swing freely from a pivot as shown below. We are going to show you. Then explain the observation. Why pendulum 1 comes quickly to rest, while pendulum 2 oscillates for some time before stopping. Now, let's go to the first part of the question. Why a metal plate experiences resistance to motion when pulled through a magnetic field? In other words, if this is the magnetic field, and here we happen to have a metal plate being pulled out of the field. We normally experience some resistance or some opposition. And that is what the question will say. So I say when a metal plate is moved in a magnetic field, the flux linking it changes and an EMF is induced. It is this induced EMF that sets up eddy currents around the path or within the metal plate. Since eddy currents flow in such a direction to oppose the motion of the metal plate, the plate therefore experiences resistance to motion. So as we are applying force in this direction, the eddy currents form a magnetic field that makes the thing to move in the reverse direction, hence opposing motion. Then the next part is that we have two pendulums. This is number 1, part A. This is part B. So I have two pendulums. Pendulum consisting of metal plates. That is pendulum A in a magnetic field. And then this is pendulum B, this is Roman 1, this is Roman 2. And the second pendulum is slotted. So this is slotted pendulum. This is just a solid pendulum. So the question was saying in pendulum 1, it comes quickly to rest as you let it swing freely. And in pendulum 2, oscillates for some time before stopping. Of course, the explanation is almost similar to the previous one. We are saying that when the pendulum oscillates in the magnetic field, the flux linking the field changes and an EMF is induced, consequently sets up eddy currents. And the eddy currents so set up act in such a direction to oppose the motion of the pendulum. And the fact that the other one is a solid pendulum, there is large amount of eddy currents that are induced and therefore damps the motion very fast. Whereas for slotted pendulum, we have laminated it and therefore the amount of eddy currents circulating in it are small and therefore they offer less opposition to the motion and therefore the motion continues for some time before stopping. Now, example to question 2, we had a diagram that shows an arrangement by which a laboratory balance is critically damped. Aluminium beam supporting the pan moves in a magnetic field as shown. You look at the pan and then explain how damping is caused. The explanations are almost the same because as the aluminium pan cuts across the field, the flux linking it changes and an EMF is induced. The induced EMF sets up eddy currents. that eddy currents oppose the motion of the beam, and therefore it is damped. And then they are saying what change will occur in the performance of the balance if the magnet is replaced by weak ones. Of course, the extent of the magnetic field, once it is reduced, the flux linking it will be smaller, and therefore the beam is going to take longer to settle because the induced EMFs will be less, and therefore eddy currents will take long to stop the motion of the beam. Want to make a conclusion here by the last question. Explain why eddy currents are useful in a moving coil galvanometer. Part B, explain why a copper plate pushed into a strong magnetic field between the poles of a powerful electromagnet. Considerable resistance to motion is felt, but no such effect is felt with a glass sheet. Then explain how damping is achieved in a moving coil galvanometer. We had previously said that eddy currents are induced current in the coil. So when the coil moves in a magnetic field, in a moving coil, eddy currents damp the motion of the coil. This makes the pointer to settle quickly, producing dead beats. So that's the role of eddy currents in a moving coil galvanometer. Then part B, when the plate moves, it cuts the magnetic field. Eddy currents are induced. The magnetic field due to current interacts with the applied field, producing a force which opposes the motion. Glass is an insulator, and therefore no current is going to be induced, hence no resistance to its motion. Lastly, about that is the B Roman 2 to explain how damping is achieved in a moving coil galvanometer. We said when the coil is wound on a conducting frame or former, when the coil rotates in a magnetic field, eddy currents are induced in the former. The magnetic field due to eddy currents interact with the applied field, causing retardation or motion. So we are ending by giving you the last activity, and there are only two numbers. They are only having two parts. So you will try to practice these numbers using the theory we have so far had, and then make submission in time, so that by the time here I know where to start from. Next time when we come back here, we are going to be talking about induced charge and ballistic galvanometer. I wish you the best of the day. Thank you for the patience and learning with me. Assalamu alaikum wa rahmatullahi wa barakatuh.